What's up, everybody? Today we'll be looking at the Einsum operator. This operator is part of the Numpy package, TensorFlow library, and PyTorch library. In TensorFlow, you could have it as tf.einsum. You could look at this documentation right here with some examples. In PyTorch, it comes as torch.einsum. Still again, we have some examples. And though they all describe the same Einsum operator, it should be noted that there are some slight differences in the way this Einsum method is called in the different libraries. Before diving deep into understanding how this operator works, it's important to know that this operator uses or takes in arrays of all sorts of dimensions, that is 1D arrays, 2D arrays, up to ND arrays. So we'll start straight up with this example with two-dimensional arrays, and we'll see how the Einsum operator can be used to replace the usual matrix multiplication. By matrix here, we're simply meaning a 2D array. In this example, we'll suppose that we have this array A and then this other array B. A is of dimension of shape 3x4, B of shape 4x5. In order for the matrix multiplication to be valid, we have to ensure that the number of columns of A have to be exactly the same as the number of rows of B. In that case, we have to ensure that generally this J has to be the same as this right here. And that's the case for this example. And so the matrix multiplication of A and B is valid. And multiplying this will give us C. But also note that the shape of C depends on that of A and B. As you could see here, if we kind of merge these two shapes and then take off this same shapes, that's this column for the first matrix and then this row for the second matrix, we would have 3x5. So we'll look at this outer values right here, this 3 and this 5, and that's what gives us the shape of the output matrix C. In general, if we have ij, jk, then we should have an output ik. So that's how we have this right here. It's very important for you to take note of the shapes whenever you're working with the Einsum operator. Okay, that's understood. Let's now dive into the code. We start by importing Numpy as np. We have that, and then we have this two matrices A and B, which we've defined already. So let's comment this for now. We have the matrix A, which is on the slides, and we have the matrix B. As you could see, printing out this will give us A dot shape, and then we could print out B shape. So we have A dot shape, B dot shape gives us 3, 4, and then 4, 5. So it's 3x4 matrix, and then a 4x5 matrix right here as B, and that's it. Now let's look for let's find the matrix multiplication of A and B. Note that in Numpy just suffices to have np to map mul. So this matrix multiplication, we pass in A and then B. So there we go, we run that, and we'll find this is the answer we get, which is correct. This is our C. So we've gotten our C. Now how can we replace this matrix multiplication with the Einsum operation? In order to do that, you just take note of this syntax right here. Notice how we have, first of all, this string right here. So we have the string, and what do we put in the string? First we have this ij, and then next we'll follow this ij. After the ij we have a comma, and then we have the jk, and then we have this arrow to ik. Now this can be read as A interacting with B to produce C. And the way we're choosing this ij, jk is such that it matches up with the shapes of A and B and with the kind of operation we are dealing with. Given that with a matrix multiplication we have A, so we're supposing it's ij, and then if we have a B, then we must ensure that the j we had here has to be the same as the j we have here. So this is just like the row. So I is the row, j the column, and here the row, and then here the column. So we have to make sure that the number of columns equal the number of rows. That's why you have this j and j right here. And then since the output is such that it takes the shape of the output is I, K, that's what we specify here. So we've taken a, b, and it's been transformed into a c. Now whatever you have before this transformation has to be passed, obviously. So that's why we have this ij. So the comma here tells us that we have this ij matching up with a, and then this jk matches up with b. So we've kind of like separated the two different arrays to be passed. And then we have this IC, which is the output we get. That's why when we print this out now, we're gonna have an output. So this IK is the output. We see clearly that this gives the same answer as just doing the matrix multiplication. Well, at this point you may be doubting, like, why do I need to do all this when I could just simply put in the matrix multiplication or np.mul ab, and then I have my answer? Well, that's a very common and normal question, and if you follow to the end, you'll see that in some examples or in many applications, you'd find that working with the Einsum operator is gonna be easier than working with the usual Numpy functions or methods you're used to working with. So let's go ahead. We've had that, and we now understand the Einsum syntax. Let's go ahead and look at many other examples. For our next example, we'll be using the Einsum operator to do an element-wise multiplication. Let's take this example right here. We have A, that's this matrix A, we have this matrix B. Obviously, for element-wise multiplication, we have to ensure that the two matrices A and B have the same shape. So as you could see from this, we print out A shape and B shape. We have 3 by 4 and then 3 by 4. Let's comment this for now. So we have this two right here, 3 by 4, 3 by 4. Let's go ahead to compute the element-wise multiplication, the Hadamard multiplication. We have that. There we go. We see that we have 2 times 2 gives us 4, 6 times 9, 54, and so on and so forth. So just simply each element on its position multiplying with its corresponding the corresponding element on the other matrix. Like if we just pick out this rundown, we have 4 times 5, 20. So that's the output here. Now in this case, you see that if we have this matrix A right here of shape ij, then B has to be of shape ij, and then the output has to be of shape ij. And so that's why you would see, let's comment this part right here. You would see that we have this input ij, or the first input ij, which is A, the second input ij, and then the output ij. So the Einsum operator automatically sees this as a Hadamard operation. So here we're gonna have the right output. Run that. Oh, let's take this off, and that's it. So there we go. We see that we have the same output as with the usual Hadamard operation or the usual element-wise multiplication. For our next, we go on to matrix transpose. So at this point, I'll urge you to like take a pause, try to come up with a corresponding matrix or the corresponding Einsum operation for the matrix transpose before continuing with the video. Now, hopefully you got it right. You have this matrix A right here, which is to be transposed. You see we have 2, 2, 1, 6, negative 2, 5, and so on and so forth. So basically we have a matrix which is of shape ij and has an output ji. In this case, we would have, say, print the Einsum transpose of A is equals the print of np.einsum. We have the np.einsum of ij, which is being transformed to ji, and then we pass in the matrix A. So let's take this off right here and then run that. There we go. We have exactly the same answer. So here we pass in A, we have this ij, no need for any commas. That's if you have to multiply, let's say we have A, B, C, D, so on and so forth, then you have, say, ij, jk, k, l, l, m. Yeah, we have 4 right here, and that's it. So now we have just 1, so we have that. Let's take this off, run it again, that's fine. So hopefully you had this correct. We now move on to working with 3-dimensional arrays. In machine learning, it's very common to have to deal with these types of arrays. Let's suppose we have this array A, which is a 3D array of shape 2 by 3 by 4. Now let's see the way we can read this. We have this whole array here, A, and then we have this two boxes in, this two arrays, this one and then this one. So that's where we have this 2 dimension right here. And now for each of this, that's for each of this arrays, we have a 2D array in it. That's for the first one, that's for this first box right here. We have this 2D array which is of shape 3, that's 1 2 3 by 4. And so that's why we have 2 and then by 3 by 4. So all this A is a 3-dimensional array of shape 2 by 3 by 4. We could generalize this as B by I by J. And then for B we have a 2 by 4 by 5 dimensional array. Now note that we have here that this B could be taken as a batch size, and this is because in general many times in machine learning computations are done on batches of data. So in this case we could have this as a single batch, that's this box right here as a single batch, and then we have this other one as another batch, giving us 2 batches. So we have the batch size equal 2. And then we may want to do matrix multiplication or batch matrix multiplication, where we want to multiply this matrix right here of this 2D array with this one and then get this corresponding output, and then multiply this one with this one and then get this other corresponding output. And we may not want to say use a for loop to say for each of this we multiply this times this to get the output and so on and so forth. We may just want to use a single operation which understands that this multiplication is done for every position in the batch. Also note that in this kinds of computations the batch dimension remains exactly the same. We have here 2 2 2, while 3 4 multiplied with 4 5 gives 3 5. So we still have this exact same value of B which is maintained everywhere. Now that said, let's go straight away into the coding. We have this 3D array A right here made of this 2D arrays, this other one, this one, and then this other 2D array. We could comment this part and then we have to print out A.shape and then B.shape. There we go. Print. And that's fine. So 2 by 3 by 4, 2 by 4 by 5. Now note that the matrix multiplication can permit us to do this without any problems. That is, we could get we could do the batch multiplications with the Numpy's matrix multiplication, as Numpy's matrix multiplication understands that when data is placed in batches like this, all we need to do is to ensure that each element in the batch multiplies a corresponding element in the batch in the other array. Now if we don't want to use this, we could also use the Einsum operator. Now the way we use the Einsum operator here is by again specifying the shapes. So we have Bij for A, and then we have Bjk for B, and then for C we still have Bik. Notice how we have Ij, Jk, and Ik, while B remains the same. So with this, we'll run this and we'll see that we have exactly the same answer for the 2 outputs. That's when we will use the matrix multiplication and when we use the Einsum operator. And still up to this point, we see that we could always, or we may not necessarily use the Einsum operator. Now what if we want to sum up all the elements in a given array? So yeah, we'll look at another different way of applying or making use of this Einsum operator. So here we have this matrix, or rather we have this 3D array A right here, and then we want to sum up all the values in that array. Here we have the sum, it gives us a value of 72. And then if we want to use the Einsum operator, what we'll be doing is we have the shapes, that's Bij, we put an arrow, and then when you don't have any output, what you're simply doing is you're summing up all the different possible values. So that's what this signifies right here. So it's just like saying we're summing up all the possible values, and then we put in, or we make sure we have the right shape of A put right here. Notice that if we do this, you see we have an error. So we correct that, we have J, run that, and that's fine. We could also sum up all elements in a given dimension or given row or given column. Say we're working with a matrix. Here we're having this Einsum. Let's just comment this. That's it. Uncomment this. Let's comment this part. Okay, so here we see that we have this matrix A, shape IJ. And now when we specify only one of this axis right here, what we're doing is we're summing up all the elements in each column, because the J is like the column. So this is the row, and then this is the column. So we're summing up all the elements in each column, and that's how we have this. We see we have 2 for the first column. We have 2 plus 2 plus 1, 5. 6 plus minus 2 plus 5, 9. 5 plus 2 plus 4, 11. 2 plus 3 plus 0, 5. So that's how we have that. So the way we understand this is we just summing up all the elements in each column. And then if we change this to I, we're summing up all the elements in each row. We'll run that. You see that for this row, we sum this, and then we sum that. Now moving to a more practical example. In this attention is all you need paper, you will have this formula right here, where we have the query multiplied with the transpose of a key. If this key has a shape of batch size by sequence length of the key by model size, and the query shape batch size by sequence length of the query by model size, then we could define this Numpy array query of shape 32 by 64 by 512 and key 32 by 128 by 512. And then what we'll do now is define the query by transpose operation, where we would have MP, the Einsum of this is considered to be, say, B, the batch size, by Q by M, and then this is considered to be, say, B by K by M. So here we would have B Q M comma B K M, which outputs B. Now at this point we have to be very careful. We have QM times KM transpose, so this becomes BQM times BMK. And now when you multiply this QM and MK, what you have is QK. So here we have BQK. Let's take it over again. We have BQM and BKM. The batch dimension doesn't matter. We can take that off. So we have this now. And then when we transpose this, we have MK. And when we multiply this, we're left with QK. So that's how we have that. And then here we have as input Q and then K. So let's run this. And when there we go, we have this output, which is of shape. We could verify shape, which is of shape QK. We have here Q, which is 64 by K, which is 128. So we have 32 by 64 by 128 output right here. Our next and final example will be inspired from the Reformer paper. In this paper, the authors explain how the data could be broken up into chunks and then they attend to each other. Again, you don't need to understand what's going on in that paper, but it's just for you to get an idea of where this problem well to present comes from. Now, supposing we have this matrix A of initial shape 2 by 4 by 8. Or to keep things simple, let's say 1 by 4 by 8. So we have a batch size of 1. We have a sequence length of 4 and a model size of 8. Here you could see this 1, that's the only single batch we have here. And then we have 4 rows and then 8 columns. B2 has a shape 1 by 4 by 4. So we have 4 rows and then 4 columns. And the paper we just saw, they further break up this data into buckets. And so right here we have 4 different buckets. Now we see that those 8 columns are broken up into separate 4x2 matrices. Here we have the 4x2 matrices. We have 4 rows, 2 columns, 4 rows, 2 columns, and so on and so forth. Now the same is done for B, with the difference that we break this 4 up. That's we break the 4 columns up into 4x1 matrices, where we have 4 columns and just, or rather 4 rows and just 1 column. In the paper, there is a task which involves taking the transpose of this B and multiplying by A. And in doing that, we are in fact multiplying the corresponding batches and the corresponding buckets. So you see that again here we have some sort of 2 fixed dimensions, and then we have this dimension or this matrix here which is actually gonna be involved in the multiplication process. And so if we have A defined as BCIJ, or the shape BCIJ, and B BCIK, multiplying the transpose of B or getting the transpose of B will give us BC, say B and C fixed, and then IK turns to KI, and A is still BCIJ. Now we have KI times IJ giving us KJ, so we have BCKJ. So if we have this 1442 by 1441, we have 1412. And now with the Einsum operator, if we have the A given as this, here we have BCIJ and this BCIK. So let's just put it in comment. So we have this BCIJ, BCIK that we had seen already on the slides. Run that. And now we're trying to find B transpose by A. So what we're gonna have here is numpy.einsum of BCIK, because here we have B transpose times A. So we have BCIK comma BCIJ, which is gonna output BC. Now at this point we recall that we're gonna have the IK, which is gonna be interchanged to give us KI. KI times IJ gives us KJ, so we're gonna have KJ just as we had in the slides, and then we pass in B and then pass in A. So we'll run that and then look at the shape. That's it. So we see that we're able to compute this very easily with the Einsum operator, as compared to the usual map mul, where we have to ensure that the matrix B is transposed correctly. So here we're gonna have mp.transpose of B, and then we have to ensure that we have 0 1, so 0 1 fixed, and then we have 3 2, because this is where we do the transposing, and then we now pass in A from this. So we have that, and then there we go. We still have the same shape. We could take this off, then run this. You see that we have the same answer for both methods, but this method looks clearly is cleaner than this one, as if we have to go to say 5 or 5D array, we'll just, let's say for example we have 6 here, and then we have 6. All we need to do here is to say for example D, so we'll put that D that way, D, and that's fine. So let's run this again. See, let's put it in shape, and that's fine. But with this we would have to say 0 1 2, and then we would have to ensure that here we have 4, and then here we have 3 for that to work. And so this is an example showing how the Einsum operator comes to make our work clearer and easier to understand. Thanks for watching. Don't forget to like and subscribe. See you next time.